Hello and welcome back to the Science of Concrete Materials class. Today's topic is the tests on Portland cement. This is lecture number 7 of the class. Today we will continue our discussion on the cement module of the class. Today's topic is the tests on Portland cement. I will cover also some tests on the paste and mortar. If you recall from the previous lecture, I have shown the tables from ASTM C150, and some information are listed, such as fineness, initial set, final set, heat of hydration, etc. These are some other requirements that the cement has to meet in order to be declared fit for the particular application. Remember what I said, that all cements at the end of the day are performance-based. So certain criteria has to be met. Cement manufacturing, as I mentioned, requires strict quality control measures, which made it necessary to establish specifications for both chemical and physical requirements. Standard tests were developed. These tests are relatively easy and can be performed rapidly. Different testing methods are used in different countries. I will cover the ASTM standards, the American standards. One thing to be aware of, you have to be careful of comparing test results, as sometimes the same property is tested using different methods. So the method of determining the property must be reported. Be aware of that. These are the tests typically performed on the cement. We have some of the the chemical properties, the chemical analysis. If you remember, we talked about it when we discussed the cement types. The standard used ASTM C114, and the compound composition determined by Bogue equations, or the direct method such as the X-ray diffraction, XRD, which I mentioned. And some chemical limits will be established based on the standards. We have also the physical properties. The chemical analysis, I will just stop on what I have covered during the cement types discussions. This lecture we will focus on the physical properties such as fineness, soundness, consistency, setting time, false set and flash set, compressive strength of mortar, heat of hydration, loss on ignition, density, bulk density, and the sulfate expansion. As I said, the chemical requirements for Portland cement, given by ASTM C150, are shown in this table, which I have shown the previous lecture, if you remember. These specifications, allow wide variations, because it has been found that cements with quite different chemical compositions may have suitable physical behavior. So the only limits placed on all types are the MgO, the magnesium oxide, the sulfur trioxides, SO3 contents, and optional alkalis contents or levels, which they become of importance if we have the potential for alkali silica reactions. Okay, and these tables also, please pay close attention to these footnotes here, as they explain a lot of the requirements and offer more explanations. As I said, we covered the chemical composition determination previously, so we will go over the physical requirements, on cements and pastes and mortar as appropriate. These are the physical requirements. the other table of from ASTM C150. Okay, so let's begin with the first property we'll talk about, which is the fineness. I have touched upon fineness previously during the talk about cement manufacturing and how it impacts cement hydration. Okay, so the higher fineness increase the rate of hydration, which in effect increase the rate of strength, and later strength basically is not affected. So as I will show a graph in a bit. The increased rate of hydration means the increased heat of rate of evolution of heat. The increased fineness decreases the amount of bleeding, but increases the amount of water required for a certain workability, which means more drying shrinkage, as we will see later. Also, the increased fineness increases the amount of gypsum required to control the set. This is due to the increased surface area of C3A available for reaction. Also, the increased cost. If you remember, grinding beyond a certain fineness will become too expensive. And that's actually what we do with the type 3. We grind type 1 finer to declare it type 3, which hydrates faster and gains strength faster, early strength. The specific area per kilogram or gram, versus particle size distribution. Two different particle size distributions may have the same surface area of the cement. Also, usually the specific area is reported. Comparison between two cements or two batches, this is what it's used for. So it is a measure of consistency and good tool for quality control and research. Okay, but it is in general practice now to describe fineness, by a single parameter. The specific surface area only is reported. So although, cements as I said, quite different particle size distribution might have the same specific surface area, it is still considered to be the most useful measure of cement fineness. Although it is possible to measure, particle size distributions, the process of measuring particle size distribution is really cumbersome, and there is still no agreement on what would constitute a best grading curve for cement. So it must be noted that, for the irregularly shaped cement particles, no two methods of measuring specific surface will give the same results. This is, partly because the different methods tend to measure somewhat different properties, and partly because the assumptions required to develop mathematical relationships for the calculations. But, for the particle sizes, it is to be noted that approximately 95% of the particles are less than 45 microns. The average diameter, roughly about 15 microns, and the particles retained on the number 200 SEV, the 75 microns opening, will never hydrate completely. Those retained on the number 325 SEV, where the 45 microns opening, will be difficult to hydrate completely. Okay. Wherever the specific surface is given, the method used to measure it must also be given, because different methods will give different values. So you have to be careful when comparing or two different cements. They must be reported using the same methodology. The real use of any given method is, as I said, is to allow comparison between different cements. And so this is really provide a good tool for quality control, as I said. This is here, it shows you the typical values. Usually type 3 has the highest fineness, followed by type 1, 2, and 5, almost the same. And this type 4 has the lowest. And if you recall, type 4, we need to control the hydration and the heat evolution, because this is low heat of hydration cement, if you remember. This graph here shows the effect of fineness on strength gain. As can be seen, early strength is greatly impacted by fineness. The 7 days, you see, when we increase the fineness, how the 7-day strength increases. The same thing with the 28 days. At later ages, the effect is not almost there. See, at the 1 year, all finenesses, almost the same strength is reported. 90 days, almost the same. There are several methods for determining the fineness. Here I will discuss two methods, the turbidimeter method and the air permeability test. You have the other method, the laser particle size analyzer, and the SIV 325, the ASTM C430. I will focus my discussion on the first two. The Wagner turbidimeter method, according to ASTM C115. This method of measuring involves the suspension of the cement in kerosene in a tall glass container. Then parallel rays of light are then passed through the container into a photoelectric cell. An image of it is shown here in this photo. The cross-sectional area of the particles intersecting the beam can be determined by measuring the light intensity. The test, is based on Stokes' law, which states that when a small sphere falls through a viscous medium under the action of gravity, it ultimately acquires constant velocity, according to this equation right here. Okay, where g is the acceleration of due to gravity, a is the radius of the sphere, d1 is the density of the sphere, d2 the density of the viscous medium, eta, this Greek symbol noted as eta, is the viscosity. So readings are taken at given times and heights below the surface of the kerosene. From these data, a specific surface area and a particle size distribution can be obtained. In these calculations, the assumptions are made that, first, the particles are spherical. Second, the flow is truly viscous. 3 particles are in the range of 0 to 7.5 micrometer. They all have a uniform size of 3.75 micrometer. So these are assumptions, and they're not all true. You have to keep that in mind. The values obtained from this method, do not correlate well with the strength of cement. However, this method does provide a fairly rapid and reproducible measure of the relative fineness of the cements. Okay? The second method is the plain air permeability, which I have done extensively during my research, according to ASTM C204. The air permeability method of determining the specific surface is based on the relationship between the surface area of the particles in a porous bed and the rate of fluid flow through the bed. The basic equation, developed by Carmen, is shown here, where, S is the specific surface area in centimeter square per gram. D is the powder density. The epsilon is the porosity of the bed, the cement bed, that is. A is the cross-sectional area. I is the hydraulic gradient. V is the kinematic viscosity. Q is the rate of flow. The Blaine method, rather than passing air through the bed at a constant rate, a given volume of air is passed through a bed of standard porosity at a steady diminishing rate, and the time required is measured, which is T, as you can see here. The specific surface S is then calculated from this relationship, which is S equals K, the constant, times the square root of the time. Here is this. The photo shows the apparatus used. So in summary, the K is the constant is not determined directly. Rather, the sample of the cement is compared to a standard sample of known surface area, usually issued by the U.S. National Institute of Standards and Technology, NIST. U.S. National Institute of Standards and Technology. So this is how it is compared to a standard sample. In summary, though, both the Wagner and Blaine methods provide an acceptable way of measuring the surface area. The Blaine value is generally about 1.8 times that of the Wagner value, probably because of the different theories involved. So the Blaine method is more commonly used, but in cases of dispute, though, Wagner method is deemed to govern. So remember that. Okay, so the requirement of the fineness. There is for type 1, 2, 4, and 5 are shown here. There is no requirements for type 3. We have a minimum value, required in meter square per kilogram. The ASTM C50 required a value of 280 using the Blaine, 160 for the Wagner. This is for these 4 cements. Typical values are between 350 to 380 for type 1, type 3 450 to 600. No limits for blended cement according to ASTM C595, or hydraulic cements per ASTM C1157. But again, values must be reported on the mill test reports. Okay. The next test is the loss on ignition. If you remember, the ASTM C114 standard test methods for chemical analysis of hydraulic cement. The loss on ignition, abbreviated as LOI. Usually a sample, how the test is done, a sample is ignited at about 900 to 1000 degrees Celsius, and then it's weighed before and after. High loss on ignition indicates usually prehydration and or carbonation. So that means either improper or prolonged storage or transportation of the cement. So this value is very important actually. and I would recommend you look for it on your test mill report. The ASTM C150 specifies a value of LOI to be less than 3%, 2.5% for type 4. For the blended cement, the ASTM C595 specifies a value of less than 3 to 5%. The hydraulic cement, ASTM C1157, no limit, but it must be reported. Okay, the next test is the density. This one is the using the Le Catelier flask, ASTM C188, the standard test method for density of hydraulic cement. As this one is shown here, the picture of the test. The range of the values typically between 3100 to 3250 kilogram per cubic meter, average about 3150. This is not an indicator of a quality. It is used for mix design, mixture proportion and calculations. And the relative density, the specific gravity of cement is 3.15. We have also another test performed as the bulk density. The bulk density is, just to differentiate it from the density, bulk density is defined as the mass of the powder divided by the volume of the space below the upper surface of the powder when it is placed in a container. The bulk density refers to the volume, including both the gaps between the constituent particles and the voids within the particles. The values varies, between 830 kilogram per cubic meter to 1650 kilogram per cubic meter. Okay. We are going to talk about the tests performed on cement pastes now. Let's talk about the unsoundness. Unsoundness in cement paste result from the excessive volume change after setting. If there is any appreciable expansion, however slow, cracking and failure of the concrete will result. So unsoundness in cement is caused by, and I mentioned this before, is caused by the slow hydration of the hard burnt magnesium oxide, MgO, or the free lime, uncombined lime, calcium oxide, and by the reaction of gypsum with C3A. This will be discussed later. These expansive reactions, I talked about these are the reaction. Basically, we get calcium hydroxide, magnesium hydroxide. These expansive reactions, take place very slowly. So unsoundness will only appear after many months or even years. So it is necessary to use some form of accelerated test so that tendencies toward unsoundness can be detected as a quality control measure. Although a number of soundness tests have been developed over the years, only one is in common use. This is the autoclave expansion test according to ASTM C151. This will detect unsoundness due to both excess calcium oxide, free lime, and excess magnesium oxide. And this is the test designated by ASTM C150. Okay. Usually how it's done, a cement paste of normal consistency, and I will define what is a normal consistency coming up now in a few minutes. A paste of normal consistency is molded and cured normally for 24 hours. The specimens are then removed from the molds, measured and placed in autoclave. The temperature is then raised so that the steam pressure in the autoclave reaches to megapascal, about 295 psi, in 45 to 75 minutes. This pressure is then maintained for 3 hours. Then the autoclave is cooled, so the pressure is relieved in about 1.5 hours. The specimen is then cooled in water to 23 degrees Celsius in about 15 minutes. Its length is again measured after further 15 minutes. And the expansion measured, the expansion must be less than 0.80% if the cement to be acceptable. So again, this is the value to look for. One thing though I have to mention and to warn you about, these accelerated tests, clearly do not simulate service condition. And the amount of expansion may be affected by a number of factors, such as the fineness of the cement, the C3A content, and others. So these tests can only serve as a guide and cannot provide absolute indication of a tendency toward unsoundness for a given cement. So this is just an indication. It's not absolutely indicative. However, in any case, they provide a valuable quality control measure, since changes in the expansion test would indicate some anomaly in the cement manufacturing process. So it is a good quality control measure for cement manufacturing process. Okay, so let's continue on the more tests on the cement paste. As I said, I'm going to talk about the normal consistency. This test method is intended to be used to determine the amount of water required to prepare hydraulic cement paste for testing. Soundness and setting and the other tests. We will look at setting time, initial setting and final, and we will define early stiffening, false set, and flash set. Okay, so normal consistency. As I said, two of the common physical requirements of cement paste, the time of setting and soundness just described above, depend on the water content of the neat cement paste. So it is necessary to define a water content at which we do these tests. This is defined in terms of the normal consistency measured according to ASTM C187. It's not written here, but here it is, ASTM C187. The test is based on the depth of penetration of a 10 millimeter diameter needle, as you can see here, under a load of 300 gram into fresh cement paste, using the Vicat apparatus shown here. A paste is said to have normal consistency when the plunger penetrates 10 plus minus 1 millimeter below the original surface, right here usually, in 30 seconds. So the amount of water required is expressed as a percentage by weight of the dry cement. The usual range being about 24 to 33%. This test is a measure of the plasticity of cement paste, although it does not correlate particularly with the quality of the cement though. So just keep that in mind. It is very sensitive to the conditions under which it's carried out, especially temperature and the way the cement is compacted into the mold. So again, comparing these results though, we're talking about here consistency, and the personnel doing the test has to be doing the tests over a certain period of time or for a certain application to ensure consistency. Okay, the setting time. As I said before, the chemical reactions that occur during the setting and hardening of cement, will be discussed later in detail. Here we will discuss only measurement of the setting time. The setting times defined here are of no fundamental significance. They merely define two arbitrary points in the general relationship between the time after the addition of water and strength gain. So two setting times are defined. The initial set, which indicates that the paste is beginning to stiffen considerably and can no longer be molded. Remember this definition. The final set indicates that the cement paste has hardened to a point at which it can sustain some load. So these are the definition. And I said these, of no fundamental significance. They're just arbitrary points, as I just mentioned. These tests are used primarily for quality control. Generally, initial set occurs 2 to 4 hours and final set in 5 to 8 hours. There are two commonly accepted test methods for determining the setting time of cement paste. They are both carried out on paste of normal consistency. The first test is measuring the time by the Vicat needle, and you can see this is a photo of a Vicat needle apparatus according to ASTM C191. In this test, the Vicat apparatus is used, except that the 1 millimeter diameter needle is used for penetration. The initial setting time is defined as the time at which the needle penetrates 25 millimeter into the cement paste. The final set occurs when the needle does not sink visibly into the paste. As you can see here, here's the apparatus, and it's molded in this mold right here. Here is the paste, and you just release the needle, and for initial set, measure the penetration. For the final set, no penetration. Just one more thing to mention also, times are calculated as the time elapsed from the point when the cement comes in contact with water. And I did not mention this earlier, but I have mentioned it here, okay? The other test though for time of setting is used by the Gilmore needle according to ASTM C266. This test is less commonly used than the Vicat test and gives different results. So you have to be careful what test is reported. The apparatus is shown here for the Gilmore needle. And here's a clearer photo of it. For the Gilmore needle, ASTM C266, the cement is considered to have acquired initial set when the initial Gilmore needle weighing 113.4 grams and with a diameter of 2.12 millimeter fails to penetrate, as you can see. Final set is reached when the final Gilmore needle weighing 453.6 grams and with a 1.06 millimeter diameter failed to penetrate. Easy. Okay, here are shown the setting times for various cements using the Vicat needle, the Gilmore needle. The Gilmore times tend to be longer than the Vicat times. Recent research has shown that setting times determined by the Vicat needle correspond closely to significant changes in the fluid properties of the paste. There is a modified version of the VICAT test can be used to determine the setting time of mortars according to ASTM C807 also. As you can see here, these are the set-in times, initial and final, for the various types of the cements. Here the C150. For the blended ASTM C595, and again 45 minutes for initial, 7 hours for final, and for the hydraulic cement according to ASTM 1157. Okay, so let's talk about the other tests I mentioned earlier, excuse me, which is the early stiffening. You know, the problem of early stiffening of cement paste may be manifested by two different phenomena. The false set, which is, this refers to the rapid development of rigidity in cement paste without the evolution of much heat. The rigidity can be overcome and plasticity regained by further mixing, but with no additional water. Typically, this is due to the hydration of the hemihydrate phase. Usually, if the sulfate present in the hemihydrate, not the dihydrate, the gypsum, it will hydrate from hemihydrate to gypsum and will cause a stiffening, but this will be overcome by mixing and workability will be restored, so it's not an issue. On the other hand, we have the flash or quick set. This refers to the rapid development of rigidity in cement paste with the evolution of considerable heat. The rigidity cannot be overcome and the plasticity cannot be regained. This is due to the rapid hydration of C3A when insufficient sulfates are present in the cement. Remember when I talked about the hydration of C3A and I said the sulfates are added to control its hydration to prevent flash set. So the cement has to be properly sulfated in order to prevent this phenomenon. The test for early stiffening, is described in ASTM C451, using again the VICAT apparatus, where a paste is prepared with enough water so that the initial penetration 20 seconds after the completion of the mixing is about 32 plus or minus 4 millimeter. The final penetration is determined 5 minutes after the completion of mixing. The results are reported as final penetration to initial penetration multiplied by 100%. This test is used to determine whether the cement complies with the requirements of ASTM C150 physical requirements. If you remember the table I have shown earlier, if you look at it on the physical requirements, you will see that. It also provides information as to whether the cement is likely to exhibit early stiffening. Although, false set may make handling and placing the cement difficult, it's not deleterious to the concrete quality. However, the problem of false set will not occur, with transit mixing, where the concrete is mixed for a long time before placing, or where the concrete is mixed prior to placement, as with pumping. The consequences of flash set are more severe and will usually cause the cement to fail to meet the time of set requirements, the table I've shown earlier. So again, this flash set will be an indication of undersulfated cement or other issues of solubility of the cement, of the sulfate, the form of the sulfate which present in the cement. So this test I consider important, and I will look for that test just to make sure this is not an issue. Okay, next test we have the heat of hydration. As you recall, we stated that the cement hydration is exothermic, and the rate of heat evolution and the total amount of heat are of importance, especially in certain conditions such as when we are pouring mass concrete sections. The heat of hydration varies greatly with the cement composition, as we have discussed earlier, especially with C3A and C3S contents being primarily responsible for high heat evolution. Fineness of a grinding is important with regard to the rate of heat of hydration, as I have shown earlier, if you remember. Finely ground cements increase the hydration rate, but the total heat of hydration at very long ages is not particularly affected. Also, the heat of hydration may be defined as the amount of heat evolved during the setting and hardening of Portland cement at a given temperature, measured in joules per gram of unhydrated cement. This measurement was most commonly done by the method specified in ASTM C186, which is the heat of solution method. Okay, so basically the heat of solution of a dry cement is compared to the heats of solution of separate portions of the cement that have been partially hydrated for 7 and 28 days. The heat of hydration is then the difference between the heats of solution of the dry and partially hydrated cements for the appropriate hydration period. However, this method is superseded by the ASTM 1702, which is the isothermal calorimetry. In this method, in this technique rather, a hydrating cement paste sample is compared to a reference sample. Keeping both samples at a constant temperature by basically taking out energy from the cement paste that is hydrating. Basically, this is a measure of the heat of hydration. The isothermal conduction calorimetry has the advantage of measuring the heat of hydration instantly. It's a powerful tool though. I have used it and it's fun. From the time of mixing of the cement with water. It is, like I said, useful technique in studying the effects of admixtures on cement, hydrating for example, or any other additive. As I said, it's a great tool in research. It can be executed with low labor input and with better precision as compared to the heat of solution method. Also, the isothermal conduction calorimetry can typically operate at a wide range of temperature and using different water to cement ratios. So the major advantage of this method, that is, it not only measures the total heat, but also records the thermal power or heat flow at different ages. The calorimeter provides the user the ability to study the hydration stages from the recorded heat curve at the desired hydration age. It's excellent. Here is the curve that you will get from the calorimetry, conduction calorimetry. It's excellent. We will study this curve in great details later during the hydration, but as you can see here, for example, this is at the addition of water. The C3 hydration basically takes place in this first stage. Dormant period we refer to here, which allow for transporting and handling of the concrete. This is the stage 3, the acceleration stage, and deceleration stage. This is the hydration of C3S. The strength gains start here. This is the steady state stage. We will go over this, don't worry, we'll go over it in detail. But using this technique, have great advantages. Like in the industry, in the concrete industry, it can be used to determine the total heat, setting behavior, quantifying retardation and acceleration. Where these peaks happen as compared to one situation to another. By this we optimize the calcium sulfate addition. If you remember, I just talked about the flash set, the quick set, and how to properly sulfate the cement. Also, we can study the influence of the calcium sulfate type, whether it's gypsum, calcium sulfate dihydrate, or the hemihydrate type, where we end up with false set. In the research area also, it's very, very helpful. We can use it, as I said, to really study the early hydration stages here within the first minute or so of adding the water, what happened. We can use it also for measuring hydration at different temperatures, because we can control the temperature. Quantifying retardation and acceleration, the influence of any additions or additives we add to the cement, proportioning of the cement-based products, the hydration mechanism of pure compounds. If you want to study the hydration of C3A, C3S, or whatever, again, this is a great tool. Again, we will talk about this curve, as I said, in later lectures, so don't worry about it for now. ASTM poses limits on heat of hydration of cement, as shown here, and as shown in the table 3.310 I shown earlier. You could refer to it. Okay. As you can see here, for example, for type 4, what are the heat of hydration at 7 and 28 days? This is option for type 2. For ASTM C595, the blended cement, this is the moderate heat. This has the suffix moderate heat. Or for the ASTM 1157, if you remember the types we discussed, it imposes these limits for the heat of hydration. For the suffix low heat, these are the limits, and the same thing, low heat for this type, the ASTM 1157. Okay, let me keep going. I think have a few more slides. I will finish them. So this lecture turned out to be longer than I planned, but nonetheless, let's talk about the mortar tests. So just again, as I mentioned, while some of the specifications, for cement require tests, done on neat paste, others, require that tests to be carried out on mortar. Since such tests will clearly depend on the type of sand used. Okay, so the mortar tests defined by ASTM all use graded standard sand. Remember this. This is a natural silica sand from Ottawa, Illinois, with the specific grading between 150 micrometers, number 100 sieve, and 1.18 millimeters, number 16 sieves. This is as defined by ASTM C778. The sand, sands from different sources may give quite different results, even though they meet the same grading requirements. Okay, so be careful. These are the tests we will cover, the mortar flow, the strength, compressive and flexural, the air content of mortar, and sulfate expansion. The air content I may not cover at this time. I probably will talk about it in some other lecture, but the sulfate expansion I will cover. So the mortar flow, as with cement paste though, many of the properties of mortars depend on the consistency or the water cement ratio. So while some specifications for mortar tests are written in terms of the fixed water cement ratio, others are written in terms of consistency. The consistency of mortars is expressed as mortar flow, determined according to the procedures of ASTM C1437. Usually, mortar is prepared with a ratio of 2.75 parts Ottawa sand, 1 part cement by weight. It is, compacted in a mold in the form of a truncated cone, 2-inch diameter, 2-inch deep rather, 50.8 millimeter, bottom diameter of 4 inches, and top diameter of 2 inches. The cone is placed on a flow table, that is, a table whose top can be raised and dropped at a height of 0.5 inches, 12.7 millimeters, by means of a rotating cam. It's a mechanical operation. It raises it, the 12.75 millimeter, and drops it. The mold is removed from the mortar and the table, is dropped 25 times in 15 seconds. The flow is then the resulting increase in the average base diameter of the mortar mass, measured as a percentage of the original diameter. Okay? The strength test. Since cement is used primarily as a structural material, its strength properties are of prime importance. So a number of strength tests have been developed to try to answer two questions. What will be the strength of concrete made with a particular cement? The second question, how do different cements compare with one another? Unfortunately, though, strength is not a very easy property to define, as will be discussed in more detail later. The factors can influence the measurement of strength, include, if you remember, I shown a slide where I said, it's easier to say what does not affect rather than what does affect the strength. So the factors that affect it, water cement ratio, cement sand ratio, type and grading of sand, manner of mixing and molding of the specimen, curing conditions, size of the specimen, shape of the specimen, moisture content at the time of test, loading conditions, and age. So the list goes on and on. In view of these many variables, it should be clear that any strength test must follow the specified testing procedure very closely. And again, as I said, consistency and care during conducting these tests. So before we examine the test method themselves, two of these variables must be discussed further, the sand and age. As I said, ever since the testing of cement began, the question has been raised as to whether strength tests should be carried out on neat paste or mortar. Although it would appear to be most logical to carry it out on the neat paste, since the use of sand, introduces a number of extra variables. Nonetheless, such tests are rarely used today. The problem with neat paste, is that it's difficult to handle and test. So more variability is introduced into the result. So it has also been found that cements that appear to be the same when tested neat may behave quite differently when used in mortar. Okay, so mortar tests provide a more reliable indication of cement quality when it comes to strength tests. The tests on neat pastes are now used only for research purposes, however, having decided to use mortar, the sand must be carefully specified as done by the ASTM standard. Again, be careful of what I said about the sand. So again, since the strength of hydrated cement increases with time, it is also necessary to specify the age, at which the test should take place. Normally, minimum strengths are specified for 3, 7, and 28 days. In addition, though, for high early strength cement type 3, there is a 1-day requirement, and for low heat cements, the type 4, which hydrate slowly, we may require sometimes having a 90-day requirement as well. The requirements of ASTM C150 are shown in the table I've shown at the beginning of the lecture, table 310 from ASTM. So you could please refer to that and see what are the strength requirements by ASTM. And again, also, when you are conducting a compressive strength test, usually you draw a curve of strength versus age or time. So one thing to remember about that, the shape of the strength-time relationship is important, not simply just excuse me, the strength at any single point. So the shape of the curve is important. The strength can be measured in compression, tension, and flexure. So we will look at the compressive strength and the flexure. Okay, like I said, the compressive strength test is by far the most measure of strength required by cement specifications. The test, is prescribed in ASTM C109, uses the test specimen 50 millimeter 2-inch cube, mortar cube. Sand cement ratio 2.75 to 1, using the standard Ottawa sand I mentioned earlier. Water cement ratio 0.485 for all Portland cements, and 0.460 for air entrained Portland cement. However, some other specifications express the water requirements in terms of mortar flow, as on the case of blended and hydraulic cements. Remember. Okay, so typically the mortar is mixed according to a certain schedule, compacted into the molds, as you can see here, and placed in a moist storage room for 24 hours. Specimens are then removed from the molds, stored in a saturated lime water, saturated lime to prevent leaching, at 23 degrees Celsius until it's tested. The samples are tested wet, using usually a machine with a spherically seated block. The load-in rate is such that the specimen will fail in 20 to 80 seconds. Okay, here are the requirements, the strength requirements for different types of cements per ASTM. This is, the Portland cement C150 standard specifications for Portland cement. And these are the minimum strength requirements reported in megapascal and PA and PSI parentheses. Okay. This is for the blended cements, ASTM C595, the various types, various ages. And this is for the hydraulic cements, ASTM C1157. Okay, the other test I will mention, I said, is the flexural test. The flexural test, which is really a measure of the tensile strength and bending, has gained popularity lately, particularly in Europe. In ASTM C348, specimens are cast in the form of 40 millimeter by 40 millimeter by 160 millimeter long prisms. The proportion and mixing of the mortar are the same as for the compression test cubes. The specimens are then tested in flexure, in center point loading, and the flexural strength is calculated. Okay. It must be remembered, though, that the strengths of mortar as determined by these tests cannot be related directly to the strengths of concrete made with the same cement. So the strength tests, on mortars serve primarily as quality control tests. Again, remember this as quality control tests. The strength of concrete can only be determined from tests done on the concrete itself. In addition, the tests and specification described here were developed for cements to be used in normal strength concrete. They do not guarantee optimum performance of high strength concretes. Okay, that's something I had to mention. Okay. The last test, though, I'm going to mention here just for completeness, is the sulfate expansion. Just generally speaking and strictly speaking, there are no really suitable tests available for determining the resistance of a cement to sulfate attack. But, ASTM C452 can provide useful information, and this is required for type 5 cements if you refer back to that table. This test measures the expansion of mortar bars made from a mixture of cement and gypsum such that the total SO3 content is 7% by weight. The mortar specimens are prepared, in the form of 25 by 25 by 285 millimeter long bars, 1 inch by 1 inch by 11 inch long, bars or prisms. Again, using graded standard sand, the sand to cement plus gypsum, in this case, ratio of 2.75, water to cement plus gypsum ratio of 0.485. Okay. After casting, the specimens are stored in water at 23 degrees Celsius, and the lengths are determined at different times. The expansion is then a measure of the sulfate resistance of the cement and should not exceed 0.045% after 14 days. Okay. This is only applicable to Portland cement, and I said the requirement for type 5, the expansion of the 0.04% at 14 days. This is instead of the limits imposed, the chemical limits, if you refer back to the physical requirements. There are limits. If this test is not performed, then there are limits imposed on these contents as per ASTM C150. Okay. All right. This is this here concludes this lecture. I know it's a long lecture, but thank you for listening, and I will see you next time. Next time we will start on the hydration of Portland cement. Those also going to be several lectures because it's a very involved topic, and I will spend a lot of time on those topics. Okay. Again, thank you for watching. See you next time.